Let yourself settle in comfortably as we journey outward from our small planet, beyond our solar system, beyond even our Milky Way, to explore the vast island universes that float in the cosmic ocean. Close your eyes and breathe deeply as we discover galaxies, the building blocks of the universe, collections of stars and gas and mystery that stretch across distances the human mind can barely comprehend. The word galaxy comes from the Greek word Galaxies, meaning milky, which refers to the Milky Way's appearance as a milky band of light across our night sky. For most of human history, people gazed at this luminous river without understanding what it truly was, a sideways view through our own galaxy, seeing billions of stars from the inside. It wasn't until the 20th century that we realized the Milky Way was just one galaxy among countless others, and that those fuzzy patches of light called nebulae were actually entire galaxies, each containing hundreds of billions of stars, floating in the vast darkness of space. This realization fundamentally changed our understanding of our place in the universe, transforming us from inhabitants of the universe to residents of one galaxy among trillions. Breathe slowly now as we consider the sheer number of galaxies in the observable universe. Current estimates, based on deep field observations from telescopes like Hubble and James Webb, suggest there are between 200 billion and 2 trillion galaxies in the observable universe. Each one is a massive collection of stars, typically containing anywhere from millions to trillions of individual suns, along with vast clouds of gas, dust, and mysterious dark matter that we cannot see, but whose gravitational effects we can measure. When you consider that each of these galaxies contains billions or trillions of stars, and many of those stars have planets orbiting them, the numbers become so large they lose meaning. Yet they remain real, a testament to the universe's almost incomprehensible scale. Let your mind drift to the 3 main types of galaxies that astronomers have classified based on their shapes and structures. Spiral galaxies, like our own Milky Way, feature graceful arms that spiral outward from a central bulge, creating a pinwheel shape when viewed from above. These arms are rich in gas and dust, making them active sites of star formation where new stars are constantly being born. Elliptical galaxies range from nearly spherical to elongated oval shapes, appearing as smooth, featureless clouds of old stars with little gas or dust remaining and minimal ongoing star formation. Irregular galaxies lack any defined shape or structure, appearing chaotic and disorganized, often the result of gravitational interactions or collisions with other galaxies. These 3 basic categories encompass the diverse forms that galaxies take across the cosmos, though astronomers have developed more detailed classification systems that recognize subtle variations and transitional forms. Now, breathe deeply and picture the structure of our own Milky Way galaxy, our cosmic home. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars from which the spiral arms emerge. The galaxy spans approximately 100,000 to 200,000 light-years in diameter. The exact size is still being refined by astronomers, and contains between 100 and 400 billion stars, though the exact count remains uncertain. Our solar system resides in a minor arm called the Orion Arm or Orion Spur, about 26,000 light-years from the galactic center, roughly halfway out from the core to the edge. The galaxy is not flat like a disk, but has thickness, with the disk being about 1,000 light-years thick in most places, though it bulges to several thousand light-years near the center. Understanding our galaxy's structure required centuries of astronomical observation and deduction, as we face the challenge of mapping a structure from within it, like trying to draw a map of a forest while standing among the trees. Let yourself relax as we explore the concept of galactic rotation. For galaxies are not static structures, but dynamic systems in constant motion. The Milky Way rotates, with stars, gas clouds, and our solar system all orbiting the galactic center. Our Sun takes approximately 225 to 250 million years to complete one orbit around the galaxy, a period astronomers call a cosmic year, or galactic year. The galaxy doesn't rotate like a solid disk. Instead, stars at different distances from the center orbit at different speeds. Interestingly, observations of galactic rotation revealed one of the great mysteries of modern astronomy. Stars in the outer regions of galaxies orbit much faster than they should based on the visible matter present. This discrepancy led to the hypothesis of dark matter, invisible mass that provides the additional gravitational pull needed to explain the observed rotation speeds. Dark matter apparently makes up about 85% of the matter in galaxies, though we still don't know what it actually is. Breathe slowly and contemplate the supermassive black holes that lurk at the centers of most galaxies, including our own. The Milky Way's central black hole, called Sagittarius A*, pronounced Sagittarius A star, has a mass approximately 4 million times that of our Sun, all compressed into a region smaller than Mercury's orbit. Despite this enormous mass, it's relatively quiet for a supermassive black hole, not actively consuming vast amounts of matter and therefore not producing the intense radiation seen from some galactic centers. Nearly every large galaxy appears to have a supermassive black hole at its core, with masses ranging from millions to billions of solar masses. These black holes seem to have co-evolved with their host galaxies, with the mass of the central black hole correlating with properties of the galaxy's central bulge, suggesting a deep connection between black hole growth and galaxy formation, though the exact nature of this relationship remains an active area of research. Now let your thoughts drift to the cosmic distance scale and how we measure distances to galaxies. For nearby galaxies, astronomers use variable stars called Cepheid variables, which pulsate with periods directly related to their intrinsic brightness. By measuring the period, astronomers can determine the star's true luminosity, compare it to how bright it appears, and calculate its distance. For more distant galaxies, astronomers use Type Ia supernovae, exploding stars that reach a consistent peak brightness, making them standard candles that can be seen across vast distances. For the most distant galaxies, astronomers rely on redshift, the stretching of light toward longer, redder wavelengths caused by the expansion of space itself. The greater the redshift, the more distant the galaxy and the faster it's receding from us. These distance measurement techniques require decades to develop and calibrate, building what astronomers call the cosmic distance ladder, with each rung depending on the accuracy of the rungs below it. The discovery that galaxies exist outside our own Milky Way came remarkably recently in human history, less than a century ago. In the 1920s, astronomer Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe what were then called spiral nebulae, fuzzy patches of light whose nature was hotly debated. By identifying Cepheid variable stars in the Andromeda Nebula, Hubble calculated its distance and proved it was far beyond the bounds of the Milky Way. It was an entirely separate galaxy. This discovery was revolutionary, expanding the known universe from one galaxy to countless billions and transforming astronomy forever. Hubble went on to discover something even more profound. Distant galaxies showed redshift proportional to their distance. meaning the universe itself is expanding, with galaxies moving away from each other as space stretches. This observation provided the first observational evidence for what would become known as the Big Bang Theory, fundamentally changing our understanding of cosmic history and the universe's origin. As you rest, imagine floating in the vast darkness between galaxies, looking at the billions of island universes scattered through space like glowing embers, each one containing billions of stars, each star perhaps with planets. And across all these incomprehensible distances, light traveling for millions or billions of years before reaching your eyes, carrying information about galaxies as they were in the ancient past. Let your breathing slow as we explore our closest galactic neighbor, the Andromeda Galaxy, also known as M31. Located approximately 2.5 million light-years from Earth, Andromeda is the nearest large galaxy to the Milky Way and the most distant object visible to the naked eye from Earth. When you see its faint smudge in a dark sky, you're seeing light that left that galaxy 2.5 million years ago, when our early human ancestors were just beginning to walk upright on the African savanna. Andromeda is a spiral galaxy like the Milky Way but larger, containing approximately 1 trillion stars, compared to our galaxy's few hundred billion. The galaxy spans about 220,000 light-years in diameter, more than twice the Milky Way's size, and its gravity influences a family of smaller satellite galaxies that orbit around it, just as small dwarf galaxies orbit our own Milky Way. Now, let your thoughts drift to the eventual fate of our galaxy and Andromeda, for these two massive galaxies are on a collision course. Astronomers have measured Andromeda's motion and determined it's approaching the Milky Way at about 110 kilometers per second, or roughly 250,000 miles per hour. In approximately 4.5 billion years, the two galaxies will collide and merge, though collision is somewhat misleading. The vast distances between stars mean that actual stellar collisions will be extremely rare. Instead, the two galaxies will pass through each other, their shapes distorted by gravitational forces, stars flung into new orbits, and gas clouds compressed, triggering bursts of new star formation. Over the course of 1 billion years or more, the two galaxies will merge and settle into a single, larger elliptical galaxy that astronomers have playfully nicknamed Mulcometa. Our Sun will likely survive this cosmic merger, though it may be flung to a different part of the combined galaxy, and by that time, the Sun will be nearing the end of its life anyway. Breathe deeply and picture the local group, the collection of galaxies to which both the Milky Way and Andromeda belong. The local group contains about 80 known galaxies spread across roughly 10 million light-years of space, though most of these are small dwarf galaxies. Besides the Milky Way and Andromeda, the only other large galaxy in the local group is the Triangulum Galaxy, M33, a spiral galaxy containing about 40 billion stars located approximately 3 million light-years away. The rest of the local group consists of smaller satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere, which orbit the Milky Way like cosmic moons. These dwarf galaxies range from a few billion stars down to just a few 100,000, some so faint and diffuse they were only discovered in recent decades. The local group represents our cosmic neighborhood, bound together by gravity while the rest of the universe expands away from us. Let yourself relax as we explore galactic clusters and superclusters, the larger structures in which galaxy groups like ours are embedded. The local group is part of the Virgo supercluster, an enormous structure containing thousands of galaxies and spanning about 110 million light-years. At the heart of the supercluster lies the Virgo cluster, a dense concentration of over 1,300 galaxies, located about 54 million light-years from us, whose gravity influences the motion of all galaxies in the supercluster, including our own local group. But even superclusters aren't the largest structures. In 2014, astronomers defined the Laniakea supercluster, an immense structure containing 100,000 galaxies and spanning 520 million light-years, within which the Virgo supercluster is just one component. The word Laniakea comes from Hawaiian meaning immense heaven, an appropriate name for a structure so vast it contains approximately the mass of 100 million billion suns. Now breathe slowly and contemplate the cosmic web, the large-scale structure of the universe revealed when astronomers mapped the positions of millions of galaxies. Rather than being randomly distributed, galaxies organize into a vast web-like pattern with dense filaments of galaxies separated by enormous voids containing very few galaxies. These filaments, which can stretch for hundreds of millions of light-years, intersect at galaxy clusters where matter is most densely concentrated. The voids between them can span 100 to 400 million light-years, regions of space nearly empty of galaxies. This structure emerged from tiny density fluctuations in the early universe, amplified over billions of years by gravity, creating the universe's largest-scale architecture. The cosmic web represents the universe's skeleton, the framework upon which all galaxies hang, shaped by dark matter's gravitational influence, pulling normal matter into these vast structures. Let your mind drift to active galactic nuclei, the extraordinarily bright centers of some galaxies powered by supermassive black holes actively consuming matter. When gas and dust fall toward a galaxy's central black hole, it forms an accretion disk, a swirling disk of material heated to millions of degrees by friction and gravitational compression. This superheated material emits enormous amounts of energy across the electromagnetic spectrum, sometimes outshining the entire rest of the galaxy by 100 times or more. The most luminous active galactic nuclei are called quasars, short for quasi-stellar radio sources, because they appeared star-like through early telescopes despite being among the most distant and luminous objects in the universe. Quasars are seen primarily in the distant universe, meaning they were more common in the past when galaxies were younger and had more gas available to feed their central black holes. Some active galactic nuclei also produce jets, narrow beams of particles and energy shot out along the black hole's rotation axis at nearly the speed of light, extending for millions of light-years into intergalactic space. Breathe deeply as we explore starburst galaxies, systems undergoing periods of exceptionally rapid star formation at rates hundreds or thousands of times greater than in normal galaxies, like the Milky Way. These intense bursts of star formation are typically triggered by galactic collisions or close encounters, when gravitational interactions compress gas clouds, causing them to collapse and form new stars at prodigious rates. A starburst galaxy might consume its entire gas supply in just 10 to 100 million years, a cosmic blink compared to the billions of years over which normal star formation proceeds. The massive young stars formed during these bursts live fast and die young, exploding as supernovae that heat the surrounding gas and can actually blow material out of the galaxy entirely, ending the starburst and enriching the intergalactic medium with heavy elements forged in stellar cores. Starburst galaxies shine brightly in infrared light, as their abundant dust is heated by intense starlight, making them prime targets for infrared telescopes. The concept of look-back time transforms how we understand observations of distant galaxies, for when we look at a galaxy 1 million light-years away, we see it as it was 1 million years ago. Light takes time to travel across cosmic distances, meaning our telescopes are time machines that show us the universe's history. The most distant galaxies visible to powerful telescopes like James Webb appear as they were over 13 billion years ago, less than 1 billion years after the Big Bang. These ancient galaxies look different from modern galaxies. They're smaller, more irregular, and more actively forming stars, showing us that galaxies have evolved over cosmic time. By observing galaxies at different distances, and thus different cosmic epochs, astronomers can piece together the story of galaxy evolution, watching how small, irregular galaxies in the early universe merged and grew into the large spiral and elliptical galaxies we see in the modern cosmos. This means that studying galaxies is inherently studying history, with every observation revealing not just where objects are, but when they existed in that form. As you sink deeper into rest, imagine the cosmic web stretching across billions of light-years, galaxies clustered along its filaments like dewdrops on a spider's web, active galactic nuclei blazing at the centers of distant galaxies, starburst systems brilliant with the light of millions of newborn stars. And through it all, light traveling across the expanding universe, carrying messages from the past, allowing us to witness the evolution of cosmic structures across 13 billion years of history. Let your breathing deepen as we explore dwarf galaxies, the most numerous type of galaxy in the universe, yet often overlooked because of their faintness. These small galaxies typically contain only a few billion stars or fewer. Some ultra-faint dwarf galaxies, discovered around the Milky Way, contain as few as 1,000 stars, barely more than a large star cluster. Despite their small size, dwarf galaxies are crucial to understanding galaxy formation and evolution. Current theories suggest that large galaxies, like the Milky Way, form through the merger of many smaller dwarf galaxies over billions of years, a process called hierarchical merging. The Milky Way is currently in the process of consuming several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, whose stars are being torn away and absorbed into our galaxy's outer halo. These small galaxies also contain proportionally more dark matter than large galaxies, making them natural laboratories for studying this mysterious substance that makes up most of the universe's mass. Now, let your thoughts drift to ultra-diffuse galaxies, a class of galaxy discovered relatively recently that challenges our understanding of what galaxies can be. These ghostly objects are roughly the size of the Milky Way in extent, but contain only about 1% as many stars, making them so diffuse and faint that they are incredibly difficult to detect. Some ultra-diffuse galaxies seem to contain very little dark matter, while others appear to be almost entirely dark matter with very few stars, presenting puzzles for galaxy formation theories that struggle to explain such extreme variations. Their discovery reminds us that galaxies come in far more varieties than the classic spirals and ellipticals we typically imagine, with nature producing exotic forms that astronomers are only beginning to catalog and understand. Breathe slowly and picture the early universe, when the first galaxies were forming from primordial gas clouds. The earliest galaxies began forming perhaps 200 to 400 million years after the Big Bang, during a period cosmologists call the Cosmic Dawn. These first galaxies were very different from modern galaxies. They were small, irregular, and chaotic, with intense star formation creating the universe's first generation of stars from pristine hydrogen and helium untainted by heavier elements. The James Webb Space Telescope, launched in 2021, was specifically designed to observe these distant early galaxies, peering back to cosmic dawn and revealing galaxies as they appeared over 13 billion years ago. These observations show that galaxies formed earlier and grew more quickly than many theoretical models predicted, forcing astronomers to refine their understanding of galaxy formation in the early universe. Let yourself relax as we explore galactic cannibalism, the process by which large galaxies grow by consuming smaller neighbors. The Milky Way has devoured dozens of dwarf galaxies throughout its history, and evidence of these ancient meals can still be found in streams of stars stretching around our galaxy. The remnants of disrupted dwarfs whose stars have been pulled apart by the Milky Way's gravity but still travel together in elongated orbital paths. The Andromeda Galaxy has been even more voracious, with evidence suggesting it consumed a large galaxy perhaps 2 billion years ago, an event that shaped its current structure. This process continues today across the universe, with telescopes capturing images of galaxies in various stages of merger and consumption. Galactic cannibalism is not violent destruction, but rather a transformation, where two separate systems blend into one larger galaxy, their stars intermingling while rarely colliding directly, and their central black holes eventually spiraling together and merging into a single, more massive black hole. Now breathe deeply and contemplate the Great Attractor, a gravitational anomaly that puzzled astronomers for decades. Observations showed that our local group, along with thousands of other galaxies, are all flowing toward a region of space about 250 million light-years away in the direction of the constellations Hydra and Centaurus, as if pulled by some enormous concentration of mass. However, this region lies behind the Milky Way's galactic plane, obscured by dust and stars, making it difficult to observe directly. Eventually, astronomers determined that the motion is caused by the Norma Cluster, a massive galaxy cluster, along with other large structures in that direction. But the mystery deepened when they realized that the Great Attractor itself is being pulled toward an even larger structure called the Shapley Supercluster, the largest concentration of galaxies in our nearby universe, containing thousands of galaxies and lying about 650 million light-years away. These discoveries reveal that galaxies participate in flows and motions on the largest cosmic scales, with their movements determined not just by the expansion of the universe, but also by the gravitational pull of massive structures across hundreds of millions of light-years. Let your mind drift to the concept of galactic recycling, the endless cycle by which matter moves between stars, gas, and the space between stars within galaxies. Stars form from clouds of gas and dust, fusing hydrogen into helium and heavier elements in their cores. When massive stars explode as supernovae, they scatter these newly forged elements back into the interstellar medium, enriching the gas from which future stars will form. Stellar winds from massive stars and planetary nebulae from dying sun-like stars also return material to space. Meanwhile, gas falls into galaxies from the intergalactic medium, providing fresh fuel for star formation, while galactic winds, driven by supernova explosions and active galactic nuclei, blow gas out of galaxies, possibly to fall back later. This circulation of matter continues throughout a galaxy's lifetime, with each generation of stars incorporating elements created by previous generations, gradually increasing the proportion of heavy elements, what astronomers call metallicity, over cosmic time. Our solar system, including Earth and our own bodies, is made from material that has been through multiple cycles of this cosmic recycling, with our atoms forged in stars that died billions of years ago. Breathe slowly as we explore tidal dwarf galaxies, small galaxies born from the debris of galactic collisions. When two large galaxies pass close to each other or collide, their gravitational interactions can pull out long streamers of stars and gas called tidal tails, resembling the tidal bulges that the moon raises in Earth's oceans, but on a galactic scale. Sometimes dense clumps within these tidal tails can collapse under their own gravity to form new, small galaxies, tidal dwarfs. These galaxies are fascinating because they formed from material already processed through previous generations of stars, unlike most dwarf galaxies that formed from primordial gas. They also appear to contain little or no dark matter, having been formed from the visible matter pulled out of their parent galaxies, providing natural experiments for understanding how galaxies behave without dark matter's gravitational influence. Tidal dwarf galaxies demonstrate that galaxies aren't static, eternal objects, but dynamic systems that can split, merge, and create new structures through gravitational interactions. The final fact for this segment concerns the galactic habitable zone, a concept that considers which regions within a galaxy are most conducive to the development of life. Not all locations in a galaxy are equally suitable for life-bearing planets. The inner regions near the galactic center contain densely packed stars, frequent supernova explosions, and intense radiation from the active galactic nucleus, making these regions potentially hazardous for life. The outer regions of galaxies have fewer heavy elements necessary to form rocky planets, as these areas haven't been enriched by as many generations of stars. The galactic habitable zone, sometimes called the Goldilocks zone of the galaxy, is thought to be an annular region at intermediate distances from the galactic center, where conditions are favorable, enough heavy elements to form terrestrial planets, but far enough from the galactic center to avoid excessive radiation and gravitational disturbances. Our solar system resides in what many consider the Milky Way's habitable zone, about halfway out from the center, in a relatively calm neighborhood where stable planetary systems can persist for billions of years, allowing time for life to develop and evolve. As you rest in deep tranquility, imagine the vast cycles of cosmic matter, gas collapsing into stars, stars forging elements in their cores, supernovae scattering enriched material back into space, new stars forming from these remains, and through it all, galaxies growing through mergers and cannibalism, pulled by invisible dark matter and vast gravitational structures, while in quiet regions, on special planets and special locations, life might emerge to contemplate the universe that gave it birth. Let your breathing slow as we explore ring galaxies, rare and spectacular structures formed through cosmic collisions of a particular kind. When a smaller galaxy passes directly through the center of a larger disk galaxy, like a stone dropped into a pond, it creates an expanding ring of star formation rippling outward from the impact point. The most famous example is Hoag's object, discovered in 1950, which shows a nearly perfect ring of bright blue stars surrounding a yellow core, separated by a gap of seemingly empty space. This ring is about 100,000 light-years in diameter, roughly the size of the Milky Way, and contains billions of young, hot stars whose blue color indicates recent formation triggered by the collision. Ring galaxies are temporary structures on cosmic timescales. The ring will eventually disperse over hundreds of millions of years, making them rare both because the precise geometry of the collision is uncommon and because they exist only briefly in astronomical terms. Now let your thoughts drift to polar ring galaxies, another exotic galactic form where a ring of stars, gas, and dust orbits perpendicular to the main galaxy's disk, like a gyroscope. These structures likely form when a galaxy captures material from a smaller passing neighbor, with the captured material settling into an orbit around the galactic poles, rather than joining the main disk. NGC 4650A is one of the best-studied polar ring galaxies, with its ring oriented nearly perpendicular to its host galaxy's plane. These systems are particularly valuable for studying dark matter because the ring's orbital speed depends on the total mass distribution of the galaxy, including its invisible dark matter halo. Observations of polar rings provide strong evidence that dark matter halos are roughly spherical and extend far beyond the visible galaxy, enveloping the entire system in an invisible gravitational cocoon. Breathe deeply and picture lenticular galaxies, a transitional type between spirals and ellipticals that feature a central bulge and disk like spiral galaxies, but lack the prominent spiral arms and active star formation. Designated with the nest 0 in galaxy classification schemes, lenticular galaxies contain mostly old stars with little gas or dust remaining for forming new stars. They appear to represent an evolutionary stage where spiral galaxies have exhausted or lost their star-forming gas, perhaps through interactions with other galaxies or the harsh environment in galaxy clusters, where hot intergalactic gas can strip away a galaxy's cold gas reserves. Lenticular galaxies are particularly common in galaxy clusters, supporting the idea that environment plays a crucial role in galaxy evolution. They remind us that galaxies aren't born into a single type and remain that way forever. They evolve, changing their appearance and properties over billions of years in response to both internal processes and external influences. Let yourself relax as we explore galaxy clusters, enormous gravitationally bound collections of hundreds or thousands of galaxies, spanning millions of light-years. The Coma cluster, for instance, contains over 1,000 identified galaxies located about 320 million light-years away. Galaxy clusters are dominated by elliptical and lenticular galaxies, with relatively few spiral galaxies compared to the field population, suggesting that the cluster environment transforms galaxies through processes like ramp pressure stripping, where galaxies moving through the hot intercluster gas have their own cold gas stripped away. The space between galaxies and clusters isn't empty, but filled with extremely hot gas, temperatures of tens of millions of degrees, that emits copious X-rays. This intercluster medium contains more mass than all the stars and all the cluster's galaxies combined, making it the dominant form of normal, non-dark matter, mass in clusters. The study of galaxy clusters reveals how environment shapes galaxy evolution and provides important cosmological information, as clusters represent the largest gravitationally bound structures in the universe. Now breathe slowly and contemplate gravitational lensing, a phenomenon predicted by Einstein's general relativity, where massive objects bend space itself, causing light to follow curved paths. Galaxy clusters are so massive that they significantly warp space, acting as cosmic magnifying glasses that bend and amplify light from more distant galaxies located behind them. This creates spectacular effects. Background galaxies can appear as multiple images, long arcs, or even complete rings called Einstein rings when alignment is nearly perfect. Gravitational lensing serves as a powerful tool for studying both the foreground cluster, whose total mass, including dark matter, determines the lensing strength, and the background galaxies, which are magnified, allowing astronomers to study objects too distant and faint to see otherwise. Some of the most distant galaxies known were discovered through gravitational lensing, their light amplified enough by foreground clusters to make them visible to our telescopes, despite forming over 13 billion years ago. Let your mind drift to the concept of galaxy quenching, the process by which star formation in a galaxy ceases or dramatically slows. Galaxies don't form stars forever. Many elliptical galaxies and lenticular galaxies show little or no ongoing star formation, filled instead with old, red stars born billions of years ago. Several mechanisms can quench star formation. A galaxy might simply exhaust its gas supply after converting most of it to stars. Interactions with other galaxies can disrupt the gas and prevent it from cooling and collapsing. Ram pressure stripping in clusters can remove a galaxy's gas entirely, or powerful winds driven by supernovae or active galactic nuclei can blow gas out of the galaxy faster than new gas can fall in. Understanding what quenches galaxies, why some continue forming stars for billions of years while others stop early, is one of the major questions in modern galaxy evolution research, with the answer likely involving a combination of these processes, depending on each galaxy's mass, environment, and history. Breathe deeply as we explore the Hubble sequence, the famous galaxy classification system developed by Edwin Hubble in 1926, often represented as a tuning fork diagram. On the left is a sequence of elliptical galaxies from nearly spherical E0 to highly elongated E7. The tuning fork then splits into two prongs representing spiral galaxies, normal spirals with tightly wound arms, SA, through intermediate SB, to loosely wound arms, SC, and barred spirals with a central bar structure following a similar sequence, SBA, SBB, SBC. Lenticular galaxies, S0, sit at the junction. Hubble called ellipticals early type and spirals late type, initially thinking this represented an evolutionary sequence, but we now know galaxies don't evolve from elliptical to spiral. If anything, spirals merge to form ellipticals, the opposite direction. Despite its historical inaccuracies, the Hubble sequence remains widely used because it effectively organizes galaxies by appearance and correlates with other properties like star formation rate, color, and gas content. The concept of downsizing in galaxy formation describes an unexpected pattern discovered through observations of distant galaxies across cosmic time. Early theories predicted that small galaxies would form first, then gradually merge to build larger galaxies, a bottom-up process. While mergers certainly occur, observations revealed that the most massive galaxies formed their stars earliest and fastest, quickly assembling their stellar mass in the first few billion years of cosmic history, then becoming quiescent with little subsequent star formation. Less massive galaxies, conversely, have continued forming stars more gradually over longer timescales, with many still actively forming stars today. This downsizing pattern, where the most massive systems formed first rather than last, was unexpected and required new theoretical understanding of how gas cooling, feedback from star formation in black holes, and mergers interact differently in galaxies of different masses. It demonstrates that galaxy evolution doesn't follow a simple universal path, but depends critically on mass, with massive and dwarf galaxies following very different evolutionary trajectories. As you sink into deeper rest, picture the universe's great diversity. Ring galaxies rippling from collisions, polar rings orbiting perpendicular to their hosts, clusters of thousands of galaxies bathed in million-degree gas, gravitational lenses bending light across billions of years. And through all this variety, the puzzle of why galaxies look and behave so differently, shaped by their mass, their environment, their interactions, and the mysterious dark matter that holds them all together. Let your breathing deepen as we explore the intergalactic medium, the vast ocean of gas that fills the space between galaxies. Far from being empty, intergalactic space contains diffuse gas, primarily hydrogen and helium, at extremely low densities, typically less than 1 atom per cubic meter, making it more tenuous than the best laboratory vacuums. This gas exists in various phases: cold, dense filaments where galaxies form, warm gas at hundreds of thousands of degrees, and hot shock gas at millions of degrees, found in galaxy clusters. The intergalactic medium contains about half of the universe's normal matter, with the rest locked up in galaxies. This cosmic reservoir provides the raw material from which galaxies draw to continue forming stars, with gas gradually cooling and falling into galaxies through filaments in the cosmic web, a process called cold mode accretion that has sustained star formation throughout cosmic history. Now, let your thoughts drift to satellite galaxies, smaller galaxies gravitationally bound to and orbiting larger ones, like moons around a planet, but on a vastly larger scale. The Milky Way has dozens of known satellite galaxies, including the Large and Small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere that contain billions of stars and orbit our galaxy at distances of about 160,000 and 200,000 light-years respectively. Other Milky Way satellites are far fainter, like the Segway 1 dwarf galaxy, which contains only about 1,000 stars and is one of the least luminous galaxies known, yet its stars orbit so fast that astronomers calculate it must contain about 600 times more dark matter than normal matter. The discovery of increasingly faint dwarf satellites continues as surveys become more sensitive, revealing that large galaxies are surrounded by extensive families of smaller companions, many of which will eventually be tidally disrupted and absorbed, their stars joining the halo of their massive parent. Breathe slowly and picture ultraluminous infrared galaxies, or ULIGs, systems emitting more than 90% of their energy in the infrared spectrum, typically outshining normal galaxies by 100 times or more. These extremely bright galaxies are almost always undergoing major mergers, collisions between two large, gas-rich galaxies that trigger intense starbursts. The prodigious star formation produces massive amounts of dust, which absorbs ultraviolet and visible light from young stars and re-radiates it as infrared radiation, making these galaxies appear relatively faint in visible light, but blazingly bright in infrared wavelengths. ULIGs were more common in the distant universe when galaxies contained more gas and merged more frequently. They represent a crucial phase in galaxy evolution, possibly representing the process by which gas-rich spiral galaxies transform into gas-poor elliptical galaxies, with the merger simultaneously consuming the gas through intense star formation and disrupting the spiral structure to create an elliptical morphology. Let yourself relax as we explore the cosmic star formation history, the story of how the rate of star formation has changed throughout the universe's 13.8 billion year lifetime. By observing galaxies at different distances and thus different cosmic epochs, astronomers have reconstructed this history. Star formation increased rapidly in the early universe, reaching a peak about 10 billion years ago, a period often called cosmic noon, when the universe was about 3 to 4 billion years old. During cosmic noon, Galaxies were forming stars at rates roughly 10 times higher than today's average. Since then, star formation has steadily declined as galaxies consumed or expelled their gas, and the universe expanded, reducing the density of matter and making gas accretion less efficient. Today, the universe forms stars at only about 3% of the peak rate. This decline means the universe is slowly fading. Fewer new stars are born each year than in the past, and eventually, after trillions of years, star formation will essentially cease as gas supplies are exhausted, and the universe will contain only aging stars gradually burning out. Now, breathe deeply and contemplate green valley galaxies, an intriguing transitional population that has helped astronomers understand galaxy evolution. When galaxies are plotted by color versus mass or luminosity, they naturally separate into two distinct groups: a blue cloud of actively star-forming galaxies with young, hot blue stars, and a red sequence of quiescent galaxies dominated by old, cool red stars. Between these populations lies a sparsely populated region called the Green Valley, where galaxies appear green due to having intermediate colors between blue and red. Green Valley galaxies are thought to be in transition, caught in the process of transforming from actively star-forming blue galaxies into quiescent red galaxies. This transition appears to be relatively rapid in cosmic terms. Galaxies don't linger long in the Green Valley, typically passing through in less than 1 billion years. Understanding what drives galaxies through the Green Valley, whether mergers, gas exhaustion, age-end feedback, or environmental effects, is crucial to understanding how galaxies evolve from one type to another. Let your mind drift to the zone of avoidance, a mysterious region of the sky where astronomers struggle to observe distant galaxies because the Milky Way itself blocks the view. This zone, centered on the galactic plane, covers about 20% of sky and is obscured by the dust and stars of our own galaxy. While we can observe nearby structures through the obscuration using techniques like infrared observations or radio surveys, very distant galaxies remain effectively invisible in these directions, creating a significant blind spot in our map of the universe. Sophisticated surveys using long wavelength observations are gradually penetrating the zone of avoidance, revealing previously hidden galaxy clusters and large-scale structures. The zone reminds us that our position within the Milky Way, while providing an inside view of one galaxy, also limits our perspective on the broader universe, leaving significant regions of space difficult or impossible to study with current technology. Breathe slowly as we explore the Hubble Ultra Deep Field, one of the most important images in the history of astronomy. In 2003 to 2004, the Hubble Space Telescope stared at a tiny patch of apparently empty sky, a region only about 1/10 the diameter of the full moon, for a total exposure time of about 1 million seconds, or nearly 11.6 days. This prolonged observation revealed nearly 10,000 galaxies in that tiny region, ranging from nearby bright spirals to incredibly distant, faint galaxies appearing as they were over 13 billion years ago. If the galaxies in this small field are representative of the entire sky, it implies the observable universe contains hundreds of billions of galaxies, each containing billions of stars. The ultra-deep field images have been used to study galaxy evolution across cosmic time, showing how galaxies looked and behaved at different epochs. The James Webb Space Telescope has since captured even deeper fields, pushing further back toward the first galaxies, but the Hubble Ultra Deep Field remains an iconic image that demonstrated just how populated the universe truly is, even in seemingly empty patches of sky. Thousands of galaxies await discovery. The final fact for this segment concerns the metallicity gradient in galaxies, a pattern that reveals how galaxies have evolved and grown. In spiral galaxies like the Milky Way, the abundance of heavy elements, metals, in astronomical terminology, decreases with distance from the galactic center. Stars and gas in the inner galaxy are more metal-rich than those in the outer regions. This gradient exists because star formation has been more active and persistent near galactic centers, producing more generations of stars that create and distribute heavy elements. The exact shape and steepness of the metallicity gradient provides clues about a galaxy's formation history. Steep gradients suggest galaxies formed from the inside out, with inner regions forming stars early, while outer regions formed later from less enriched gas. Flatter gradients might indicate significant mixing through processes like radial migration, where stars and gas move inward and outward, or might result from gas accretion from the intergalactic medium diluting the metallicity. By studying metallicity gradients in many galaxies at different distances, astronomers can test models of how galaxies assemble their mass over cosmic time. As you rest in complete peace, imagine the universe's vast timeline. Cosmic noon 10 billion years ago, when star formation blazed far brighter than today. Galaxies transitioning through the green valley from blue to red. The ultra-deep field revealing thousands of galaxies in a patch of sky smaller than your thumbnail held at arm's length. And everywhere, the patterns of metallicity recording billions of years of chemical enrichment. Each element in each star a clue to cosmic history. Let your breathing slow as we explore globular clusters, ancient spherical collections of stars that orbit galaxies like satellites, but on a smaller scale. These compact stellar cities contain hundreds of thousands to millions of stars packed into regions only tens to hundreds of light years across, making them far denser than typical galactic neighborhoods. The Milky Way hosts about 150 known globular clusters, with some orbiting in the galactic halo at distances of hundreds of thousands of light years. What makes globular clusters particularly fascinating is their age. Most are 10 to 13 billion years old, nearly as old as the universe itself, containing some of the first generation of stars that formed in our galaxy. Their stars are uniformly old and metal-poor, having formed from primordial gas before many stellar generations had enriched the interstellar medium with heavy elements. Globular clusters provide living fossils of the early universe, allowing astronomers to study ancient stellar populations and test theories of stellar evolution and early galaxy formation. Now, let your thoughts drift to the phenomenon of ramp pressure stripping, a process that dramatically transforms galaxies moving through galaxy clusters. As a galaxy plunges through a cluster at speeds of hundreds or thousands of kilometers per second, it encounters the hot, diffuse intracluster medium. Despite the thinness of this gas, the galaxy's rapid motion creates a ramp pressure, like the wind you feel when driving in a convertible, that pushes against the galaxy's own cold gas. This pressure can be strong enough to strip the cold gas completely out of the galaxy, blowing it backward like a cosmic tail and leaving the galaxy unable to form new stars. Spectacular images have captured jellyfish galaxies, with long tentacles of gas and young stars trailing behind them as they move through clusters, frozen in the act of being stripped. This process helps explain why cluster galaxies are predominantly red and quiescent, They've had their star-forming fuel violently removed by the hostile cluster environment. Breathe deeply and picture barred spiral galaxies, spirals with the prominent bar-shaped structure of stars extending from the central bulge. About 2/3 of spiral galaxies, including our own Milky Way, possess such bars. These bars aren't static structures, but rotating patterns that can drive gas inward toward the galactic center, potentially fueling central star formation or feeding the central supermassive black hole. Bars are thought to form through gravitational instabilities in galaxy disks and can influence the evolution of spiral structure. Interestingly, observations of distant galaxies show that bars were less common in the past. Only about 20% of spiral galaxies had bars 7 billion years ago, compared to 2/3 today. This evolution suggests that bars form and dissolve over cosmic time, possibly triggered by interactions with other galaxies or by processes within the galaxy disk itself. The presence or absence of a bar can significantly affect the galaxy's evolution, altering how gas flows through the disk and influencing where and when stars form. Let yourself relax as we explore safer galaxies, a class of active galaxies named after astronomer Carl Seyfert, who first identified them in 1943. Safer galaxies are spiral galaxies with extremely bright nuclei that emit as much light as billions of stars from a region only light days or light weeks across, far smaller than the galaxy itself. Unlike quasars, which are so luminous they outshine their entire host galaxy, safer galaxies are bright enough for astronomers to also study the surrounding normal spiral galaxy. These bright nuclei are powered by accretion onto supermassive black holes, just like quasars, but at lower rates. Safer galaxies are relatively common in the nearby universe, with about 10% of bright spiral galaxies showing safer characteristics, suggesting that many or perhaps all galaxies go through active phases when their central black holes feed actively. The study of safer galaxies has been crucial for understanding active galactic nuclei and the relationship between supermassive black holes and their host galaxies. Now, breathe slowly and contemplate dark galaxies, hypothetical galaxies composed almost entirely of dark matter with few or no stars. While ultra-faint dwarf galaxies and ultra-diffuse galaxies contain very few stars relative to their dark matter, a true dark galaxy would be effectively invisible, detectable only through its gravitational effects on nearby objects or through the faint glow of any minimal hydrogen gas it might contain. Several candidate dark galaxies have been proposed, including clouds of neutral hydrogen HI that rotate as if embedded in massive dark matter halos but show no signs of star formation. The existence of dark galaxies is predicted by some cosmological simulations in a universe dominated by dark matter. Some dark matter halos might fail to accumulate enough normal matter or might have that matter stripped away, leaving behind dark matter structures without visible galaxies. Confirming the existence of dark galaxies would provide important insights into galaxy formation and the nature of dark matter, though their very invisibility makes them extraordinarily difficult to detect and study. Let your mind drift to the stellar halo of galaxies, the spherical region of old stars, globular clusters, and stellar streams that surrounds the visible disk. The Milky Way stellar halo extends perhaps 300,000 light-years from the galactic center, far beyond the main disk's edge. This halo contains relatively few stars compared to the disk, perhaps 1% of the galaxy's stellar mass, but it tells important stories about galactic history. The halo is populated primarily by debris from ancient dwarf galaxies that the Milky Way has consumed over billions of years, with streams of stars marking the disrupted remains of these meals. The halo stars are generally very old and metal-poor, having formed in small galaxies before being accreted. By mapping the structure and chemistry of halo stars, astronomers can reconstruct the Milky Way's merger history, identifying which dwarf galaxies were consumed when, effectively doing galactic archaeology. Every large galaxy possesses such a halo, built up through hierarchical merging, with each halo encoding that galaxy's unique accretion history. Breathe deeply as we explore the concept of galactic winds, massive outflows of gas driven from galaxies by stellar and black hole activity. When numerous massive stars form in a starburst galaxy, they live briefly and die violently as supernovae, heating surrounding gas and creating expanding bubbles of hot material. If enough supernovae explode in a concentrated region, these bubbles can merge and blow through the galaxy's disk, driving a wind of enriched gas into the intergalactic medium at speeds of hundreds of kilometers per second. Similarly, active galactic nuclei can drive powerful winds through radiation pressure or through jets that interact with surrounding gas. These galactic winds are crucial for galaxy evolution. They remove gas that would otherwise form stars. They regulate the growth of supermassive black holes by removing their fuel supply, and they enrich the intergalactic medium with heavy elements, distributing the products of stellar nucleosynthesis across vast regions of space. Without galactic winds, theoretical models predict galaxies would be far more massive than observed, suggesting these outflows are essential for understanding why galaxies have the masses they do. The Tully-Fisher relation, discovered in the 1970s by astronomers Brent Tully and Richard Fisher, reveals a remarkable connection between a spiral galaxy's rotational velocity and its total luminosity. Galaxies that rotate faster are intrinsically more luminous, following a tight correlation that holds across a wide range of galaxy masses. This relationship exists because both rotation speed and luminosity depend on a galaxy's total mass. More massive galaxies have deeper gravitational potential wells, causing faster rotation, and they also contain more stars, making them more luminous. The Tully-Fisher relation is valuable for measuring distances to galaxies. By observing a galaxy's rotation speed, which can be measured regardless of distance, astronomers can infer its intrinsic luminosity, compare it to observed brightness, and calculate distance. This technique has been used to map the large-scale structure of the nearby universe and to measure the Hubble constant, the expansion rate of the universe. The existence of such tight scaling relations suggests that galaxy formation follows remarkably regular processes, with the properties of spiral galaxies determined primarily by their mass in predictable ways. The final fact to contemplate as you drift into the deepest sleep concerns the far future of galaxies, billions of years from now, when the universe will look very different than it does today. As the universe continues expanding and star formation declines, galaxies will slowly fade as their stars age and die. In 1 trillion years, most star formation will have ceased, and galaxies will be filled with old red stars, white dwarfs, neutron stars, and black holes, with few new stars being born. The Milky Way and Andromeda will have merged into a single galaxy, and local group dynamics will have pulled some nearby galaxies into the merged system, while cosmic expansion carries more distant galaxies beyond the cosmic horizon, forever unreachable. Eventually, in timescales of 10 superscript 1 years or more, even the longest-lived stars will burn out, and galaxies will become graveyards of stellar remnants slowly orbiting in the darkness. Through quantum effects like proton decay or Hawking radiation from black holes, even these remnants might eventually evaporate. Yet even as galaxies fade and disappear, they will have served their purpose, creating the structures in which stars could form, heavy elements could be forged, and perhaps, in special places and times, life could emerge to contemplate the vast cosmic story of which it is a part. As you rest in the deepest tranquility, let the story of galaxies wash over you. From their birth in the early universe through billions of years of growth and evolution, merging and transforming, creating stars and planets and elements scattered across space in the cosmic web, each one a universe unto itself, and all of them together forming the grand structure of the cosmos, while you, made of atoms forged in ancient stars, belonging to one small planet, in one solar system, in one galaxy among trillions, drift peacefully towards sleep, a brief moment of consciousness in the vast river of cosmic time.